Good afternoon, everyone. LIGO-India is back with another behind-the-scenes Gravity Matters interview. There's been a lot of talk of the recent GW discovery of a mystery object that falls within the mass gap. And the mass gap is basically the gap between the heaviest neutron stars and the lightest black holes. Today, we have a very special guest, Dr. Shanika, who played a significant role in the discovery of this exceptional GW event. And Dr. Shanika completed her PhD from Monash University in Australia, where she researched on the population properties of black holes and neutron stars, the emerging picture of gravitational wave astronomy. She is now a postdoctoral researcher at the Observatoire de la Côte d'Azur, Lagrange Laboratory at Nice in France. She's also a member of the LIGO Virgo Cabra collaboration as a part of the Virgo Artemis group. Using gravitational waves, she studies populations of compact binaries to explore the formation of mechanisms and the stellar evolution processes of these systems. And in addition to her research, Dr. Shanika is passionate about science communication and volunteering. She's a part of the Space Australia team and the Include Her Movement campaign. With that, I would like to welcome you for this exciting interview, Dr. Shanika.
Thanks for having me.
Okay. So I'll start with a very basic question. If you could describe your journey of becoming a researcher in gravitational wave astronomy field, and what were the key steps or decisions that were involved?
Yes, I can definitely expand on that. So yes, I'm currently a postdoc at the Observatoire de la Côte d'Azur. However, the journey to becoming a gravitational wave astrophysicist has been interesting, but also not that unique, I would say. So really starting from the beginning is early childhood. Being interested in astronomy, I was very interested in planets when I was really, really young. I would go to the local library with my parents, and they would let me borrow books on the planets in the solar system. And this was primary school. But then I kind of let that go. Even though I was interested in space, I kind of gave up on it in the sense that I thought the only career you could do with astronomy is become an astronaut, and I didn't want to go into space. I am still scared of the idea of leaving the ground, so I'm very happy to put my feet on the ground and learn about space from here. But yeah, so I kind of just went, okay, space is a hobby. Space is a hobby. And then early high school, I thought I was going to go into medical health sciences because that's kind of what I saw my peers doing, especially with my background and like the people that I've seen before me do was health sciences, and thought, okay, I'll just do health sciences. I was good at biology and chemistry as well, so it just felt like a natural progression. And then I moved schools, and I had this excellent physics teacher who noticed that I really, really liked physics. Like, I really liked it. And I would take any opportunity to create, like, any projects that came about, I would try to make them space related if possible. And she pretty much told me, if you're interested in physics, Shanika, just do it. Like, this is a career that you could do. It feels silly to say this, but it really was a light bulb moment. It was really kind of the starting point for me of actually taking it seriously and going, this is a career that I could actually do. So that was like the start. And then I went on to do physics, chemistry, maths, and astronomy in university. I did my bachelor's degree at Monash University as well. Also, I did like all of my schooling in Australia in Melbourne. So from my primary school, I was born in Melbourne, Australia. So I lived my entire life up until my postdoc in Melbourne. But yeah, like doing my bachelor's at Monash University as well, doing that. And then I did a research project in my final year of undergraduate degree, and I did it on neutron stars. So I thought it was a really interesting project. It was looking at X-ray pulsations of these sources that might be continuous gravitational wave candidates, which is a different area to what I work in now. But essentially, that was kind of also another tipping point for me in terms of physics or astrophysics, because physics is also really, really cool. Like you have quantum physics, condensed matter physics, particle physics, like all these physicses. And I thought, how am I supposed to pick? So this research project actually helped me pick. And I kind of made peace with myself in terms of, okay, neutron stars are really, if you think about it, they're high energy physics labs in space. So I thought, okay, this is how I'm getting my physics and astrophysics at the same time. It's okay. And then, I mean, this was, wait, which year was this in? I have to remember. So this is 2017, my research project. And so gravitational wave astronomy and like the discovery of GW 150914, which was the first gravitational wave detection we saw, was only just like announced in 2016. So this is a field that was born during my undergraduate years. So I couldn't have imagined, like even like high school and so forth, of working in this field. So I learned more about it because I was part of the gravitational wave group at Monash while working on this undergraduate research project. And then I continued this research project into honors. And then I realized, you know what? Gravitational waves seem pretty cool. And so I essentially moved from one supervisor to another. So Duncan Galloway was my honors supervisor, who is expert on all things neutron stars. And he pretty much told me, don't get too comfortable. You you want to do gravitational wave astrophysics. You should really pursue it. So I did. And then my PhD supervisor, Eric Thrain, was, happy to take me aboard as his PhD student. And so I did my PhD at Monash as well. So I really stayed in the one spot for a long while. And then the PhD was during a pandemic, so that was quite interesting and tough at times. But I am quite happy now that I've actually left Melbourne for a bit and I'm seeing more of the world and doing research pretty much on the other side of the world when I think about it.
Yeah.
At the Observatoire de l'Occultation with this fantastic group. So I'm part of the Lagrange group formally, but I also work with the Artemis group, which is part of the group that works in the Virgo collaboration. So it's quite nice to work with astrophysicists and astronomers, but also gravitational wave astrophysicists, and trying to find connections between what we can do in terms of understanding the corpses of these objects, these stellar objects like black holes and neutron stars, but like, how did they come to be? These are the kinds of questions that I'm very interested in. So long story short, it was an interesting journey, but like I feel like the progression, I didn't have a huge amount of decision making to do. It's more people kind of pointed out, you're interested in this, just do it. So that's how I somehow ended up here.
But it's amazing to see how your hobby actually went on to become your passion and then eventually your career. It's amazing.
Yes,
It's really nice.
I think primary school me would be mind blown at where I am today, which
I think this is the most important thing, right? Like you have to be happy with where you are right now. So
yeah, wow. Absolutely.
That's great. So we'll move on to the next question, and I think the audience would like to know if you could describe about your involvement in the recent discovery of the object with the mass that lies within the so-called mass gap, and what was your role in this discovery?
Absolutely. So yes, we recently announced the discovery of GW 230529. So when you're a gravitational wave astronomer, by the way, these numbers really do roll off the tongue. I'm kind of lying here. If you've seen the event a bunch of times, then they kind of become you won't forget them, is all I'm going to say. So yes, GW 230529. So we detected it in 23 in May on the 29th day of that month. And this event was interesting because the more massive object lies in this region known as, we call the mass gap. So historically, observations of galactic binaries and the measurements, dynamical measurements of these things seem to indicate that there was no compact objects between the masses of, say, 3 to 5 solar masses, roughly. And this is the region between the masses of neutron stars and black holes, as you explained before. And I mean, since then, there have been observations of objects that are kind of filling this gap, but the question still remains of, is this region just less populated, and what does that mean in terms of the formation of these systems? So this object really kind of was one, the gap is definitely not empty, both in electromagnetic observations and gravitational wave observations. It really strengthens that argument. But also, some of the analyses seem to suggest maybe there isn't a gap-like feature at all. It might, I mean, it's possible for it to be completely filled. I think we need a few more observations to be sure, but right now, this event being there is kind of throwing into question how black holes form. So I should say this event is most likely a black hole paired with a neutron star. And I say most likely because there is some possibility that it could be a neutron star because the mass range is between 2.4 and 4.4-ish. But most of the support for that measurement is at around 3.6. So we don't know the maximum mass of a neutron star. I think observations put it at around 2.1-ish, but theoretical predictions can be pushed up as far as, I think, 2.8, 2.9, depending on what theoretical model you look at. But there is a possibility, if it's in the tail of the distribution, that it could be a neutron star. But it's very, very most likely to be a neutron star paired with a black hole. So it throws into question how these systems form. For example, how do you form such a low mass black hole? And this relates to, okay, do you have a neutron star that was able to accrete matter and become a black hole? Or does the explosion mechanism of the initial star have a lot of matter that just falls back onto the object to become a black hole? So these are the kinds of questions that were raised, but also what's cool about this event is that it's the most symmetric neutron star black hole merger we've seen to date. So we've seen neutron star black hole mergers before. There were two. And this one, most symmetric meaning closest in mass. The mass ratio is closer to 1 than everything else. And what this gives is the possibility of tidal disruption. So when you've got something like a neutron star, you can actually distort it with the gravitational pull of the black hole. It can be pulled, and if they're in similar masses, the black hole is small enough to actually rip the neutron star apart instead of it being completely swallowed immediately. So if it's completely swallowed immediately, you're not going to see any light. But if it's ripped apart violently, which is a pretty awful way to go for the neutron star, but you'd be able to see light from this object. And so this is actually something that would have been, if we had a really good localized source, it would have been an interesting event to follow up. Unfortunately, this event was only detected with a single detector. So when you try to localize it on the sky with a single detector, that's quite hard. So if you look at the localization map, actually, it's pretty much the entire sky. So that's not great for our electromagnetic astronomer friends to actually follow these things up. So what we need is more detectors observing at the same time to do this. And O4b just recently started. It's the 25th of April today. So it started on the 10th of April. And you look at the sky maps now with LIGO, Hanford, Virgo, LIGO, Livingston. the sky maps when you've got all three detectors is beautiful. Just a small region of the sky, follow-up is great. So I'm really hoping that we have observations of maybe even a BNS, I hope, with all three detectors on. I know there's a lot of people really wishing for a BNS. But I also mentioned there was a recent alert that came out actually that might be an NSBH. There's still ongoing analyses that need to be done, but this public alert was a well localized source, looks to be an NSBH, and I'm pretty excited.
Sorry, could you just say the full form so the audience gets to know and maybe give a brief about it, like BNS and all of that?
Oh, yeah, sorry. So yeah, BNS, binary neutron stars, so two neutron stars going around in a binary, and NSBH being neutron star black hole paired together. And so if you've got two neutron stars paired together going around each other, not only do you get gravitational waves, but you also get light as well. I tend to get a little bit carried away.
It's okay. No problem.
These things. Stop me at any time. But yes, I wanted to mention, like, there was a recent alert that came out with a really good localization on the sky. Might be an NSBH. We need to wait and see what LIGO, Virgo, Cagra collaboration folks do. But essentially, it's an exciting time to be doing gravitational wave astronomy. I mean, it's always been exciting, but it's extra exciting when you've got deeper sensitivities and so forth. So going back to your question, what was my involvement with this paper? I work on studying populations of these sources, of compact binaries. So compact objects are black holes and neutron stars. And so the great thing is when you have a bunch of detections is that you can start asking questions about the population as a whole. So, for example, most of the stuff that I've worked with actually is binary black hole mergers, so BBHs, and that purely because we have so many. Actually, I have a poster up here from my days in OSGRAPH, but essentially it's showing all the 90-ish detections from up to the end of the third observing run. So when you have a lot of these events, you can start asking questions about the general trends of the population. For example, how fast are they spinning? Are they all aligned in a particular direction when they're spinning? What's the maximum mass of the population, and so forth? Because answers to these questions do tell us a little bit about how they might have formed and evolved. And so that's my main area of research, trying to understand how these systems came to be. And so my role was actually as a member of the paper writing team. So you've got the whole collaboration of people, with input, but you also have a team that's dedicated to write the paper. And my role was very much helping with the population descriptions and discussions, but also generating the figures, because I really like making things look aesthetic. So all the plotting, helping with preparing the data release and so forth. So a little bit of admin things, but also doing the populations discussions as well. So it was, but I have to stress, like, these things take huge amounts of effort from many people across the collaboration, from all the way from detection to the paper writing. Like, we're at the end of the chain. Like, there's so much that's done beforehand in terms of detection, analysis of the data and data quality, all those things, all the way down to actually writing up the paper and submitting it. So it was honestly like such a great opportunity to be able on a discovery paper of this event. So hopefully people are reading the paper.
Yes, I think they will now after they have a look at your interview. So, okay, so next question is, what were some challenges you faced while pursuing your studies, and how did you overcome them? In general, you can list a few.
Yeah, great question. It hasn't been smooth sailing. So I talked about, how my passion allowed me to get to this point, but it hasn't been a smooth sailing. So during my undergraduate degrees in particular, mental health is like an important thing that needs to be discussed, and I think it's good to be open about these things. So um, I have anxiety. I think a lot of us actually suffer from anxiety, but it might be not well understood in terms of how you work and so forth. So for me, it came to a point where I was just pushing ahead and ahead and ahead, and then I just crashed. Crashed in the sense of I was just unable to focus in exams. I just got anxious to the point where I just couldn't sit exams anymore or do any timed assessments. And so this led to me not being able to just pass courses, because exams tend to be a huge component of the weighting for a subject. My handed in assignments and everything always got really, really good marks. But when it came to those timed assessments, I would panic, have panic attacks, and it got to a point where it just wasn't happening. So I decided to just, okay, this is not working, Shanika. You're going to reduce the amount of units you're doing and work your way up again, because this needs to be dealt with. And so I got the help that I needed, the support structures were there. I was very, very lucky to have a group of people in the department, admin staff, who actually noticed something was up, and they pretty much said, hey, Shanika, maybe you should see a counselor, maybe you should seek help. I'm like, okay, I really should. and and I did, and it really helped me work through some of the issues that I was dealing with. A lot of like external factors influenced like what I was going through at the time, and having that support network really helped me progress. Because if I had tried to keep at the mentality I had at the time was, I can't delay my studies. I need to finish this as quickly as possible because delaying studies is bad. That's a load of rubbish. You do what you can and at your own pace, because science is always happening, right? Like you're not missing out by trying to accelerate to the finish line. Like just breathe, take it at your pace, and enjoy it. And that's a learning curve that took me a while, because I was just stressed. I need to finish the degree. I need to finish this degree. But my mentality shifted once I had that experience, essentially. And luckily, this happened before honours. So it didn't impact my marks in honours, because I'd gotten the help, recovered, and slowly gotten back into the rhythm of my studies, and was able to qualify for honours and then qualify for a PhD. So I guess in a way, I crashed and burned at the right point in time. It happened early enough that it didn't impact my later studies. And I mean, the great thing about research is you don't have exams. So some of us, I think, are more inclined to do better at research than exams and things like that. I'm very much enjoying research in terms of being able to just work at my own pace. I mean, of course, there are deadlines and things like that. It's especially when you're writing a paper for a collaboration, you've got to hit these deadlines, but it's not panic level of exams. So yeah, so in terms of like my progression, definitely hit a wall in undergraduate, but was able to overcome it with the support structures. I was very, very lucky that I had such a supportive department, as well as supervisors and people, lecturers in the courses, who were very sympathetic to my situation. And so I was able to progress. But that was like the main kind of thing that happened. In terms of struggles, I think a lot of us struggled during the pandemic. Of course, it was a global thing. Melbourne in particular, we were locked down for a while. I think we had some of the longest lockdowns. While as an astrophysicist, that doesn't really impact my research. I can still work on my laptop, study, some of the most extreme objects from my laptop, which still blows my mind, honestly. But it's the human factor that really that loss is really, really hard, because on campus, you're chatting to people face to face. You go for a coffee run, or hot chocolate in my case. I don't drink coffee. Hot chocolate's the best thing. I'm really trying to push this hot chocolate agenda everywhere I go. But it's those coffee runs, hot chocolate runs that really, helped you kind of just have the good moments. And also, one of the things I really, really liked, and I still like doing, is outreach and also teaching, but outreach mainly. And that factor was gone. You can't really do in person outreach, face to face, interact with kids or students. And that's an aspect that I really, really enjoy and keeps me kind of motivated and energized to do things as well as my research. So that period was really, really hard. But I'm very, very thankful that Melbourne got through. Like the lockdowns were there to protect people, and so I'm grateful for that. But that was definitely a hard period of not being able to interact, but also not being able to travel to international conferences and things like that. So this is like worldwide kind of issues, and so but it we all persevered, and we're here. So it's there's always going to be highs and lows. You just gotta stick with it, and if you have a good set of friends, colleagues, it just makes it a little bit easier.
True. Thank you for sharing about your undergraduate anxiety issues, because I think a lot of us face that. I mean, me, myself, students my age and around me, I can see that happening. So it's important to talk about.
Yeah, it's the I think an aspect of it, just to expand on this, is like the external pressures you get that
Yes.
I just they shouldn't be there. Like the pressures you put yourself under for just trying to get things done at a certain time, and sometimes unrealistic expectations of yourself. Um, I think a lot of us are a little bit too hard on ourselves at times. So it's important to just step back and go, okay, what am I doing and why am I doing this? Well,
Yes.
what am I doing? Astrophysics, and why am I doing it? Because I like it. So I'm going to do it at my own pace and do it while I like it. So that's the kind of mentality that I've reached getting to my postdoc. I'm going to enjoy it while I can, whether I stay in academia or not. It's just going to be, I'm going to do it while I still enjoy it. And I think that's a good approach.
That's a great approach, actually, and it's simple too. So nice. I mean, it's a good advice for a lot of us. So thank you. And okay, so we'll move on to the next question. I think this may be a little connected to the previous one, but for young students aspiring to enter in the field of gravitational wave astronomy, could you share some tips based on your experience?
Tips. Okay. So for me, yeah, well, so I got into gravitational wave astronomy kind of just, I had the right background. So physics, maths, astronomy. I would say in hindsight, what hindsight, I wish I did a major in astrophysics and maths instead of astrophysics and physics. The reason I did astrophysics and physics because I couldn't decide between the two. But in hindsight, if I had just picked one, I should have picked maths, because you do need a certain level of maths to be able to do some of the problems, study some of the problems you do in gravitational astrophysics. It's a good background. You don't need a major in maths, but it's definitely useful. What else? What else? What else? Yeah, essentially, if you have a good foundation in undergraduate astrophysics and maths, it makes it a lot easier to understand the concepts in gravitational wave astronomy, but also coding. I think this comes up a lot more these days. Like up until my undergraduate research project, I hadn't done any coding, like any coding. And my first experience with coding was C. I Most of that research project was me learning how to code. It was painful because it was just trying to answer research problems while trying to learn coding on the fly, but also trying to understand code written by someone else that I didn't have contact with. So it was definitely a challenge and a very steep learning curve. So now I work pretty much just with Python. There might be other languages on the horizon, but right now, Python. It's a great introductory language. So if you're interested in doing astrophysics in general and gravitational wave astronomy, well, at least my area, you do lots of coding. My day-to-day is really coding, making plots, coding, making plots. So, and the occasional writing up of these results, but mainly, I'll be opening a terminal every day to code things. So it's definitely a good background to have, especially if you're early, university or even in high school. Doing some sort of coding thing is great. And I think this is more of a thing just generally, like the way everything is moving, both academia and industry. This is an essential skill, just like being able to write. Coding is very, very important. So the recommendation I get is coding, but also making sure you have astrophysics and maths in your undergraduate degrees. Of course, it depends on which area of gravitational wave astrophysics. So, well, I work in gravitational wave astrophysics, so astronomy was good. But if you're working more on the instrumentation side of things, I think a good basis is actually physics and understanding that area of like instrumentation as well. So it really depends on exactly which area of gravitational wave physics, astrophysics you want to go into.
To actually ask a little more on this question, if you were to suggest some, say, research projects that students can take during their high school or undergraduate years, what would you suggest them to work on so that they get a grasp of what is actually gravitational wave astronomy?
Good question. I guess, part of it is depending on what's available around you, in terms of different programs, or like at your high school or university sometimes. For me at university, there were research projects offered that were kind of related to the field. I imagine like there are some occasional like workshops that are done by the collaboration that kind of like showcase what gravitational wave astronomy is all about. So if there are events like that, I would definitely try and look into those, because that gives you an idea, especially from gravitational wave astronomers, exactly what we work on. But yeah, and I find myself watching a lot of YouTube videos as well, just to get to know like what people are working on. Like this series is pretty good to get to know different areas of gravitational wave astrophysics. So, but to get actually involved, I think workshops are a good way to go about it, because it's a very hands-on, working with data kind of thing. So if you see those, apply, because they're good. But I can't think of exactly what the events are called, because I can't remember.
So they're actually called gravitational wave open data workshops.
That's it.
I think, the website is gwosc.
See, I should know this because I was a mentor at one of those for parameter estimation. So. Yes, but it's called the Open Workshop. You're right, and so that one definitely hands-on experience and it gives you a really good introduction into understanding. Well, actually, how do we do these analyses? How do we extract the information about these compact objects from the gravitational wave signal? And what assumptions go into it? Because there's a lot of assumptions. So, absolutely. Open data workshop. Look into it. I would say that's more targeted. You definitely do need to have a coding background, though, to be able to get the most out of those workshops.
Right. Okay, yes, I think that answers like the basic tips, like yes, coding, mathematics, and then trying out your own workshops.
Yeah.
Okay. So this is the last one. So how do you approach research problems like those in gravitational wave astronomy, where there's often limited information that is available?
What do you mean by limited? Can you expand on that?
What I mean is, so there's a certain set of data that comes from the detectors, right? And how do you interpret with just that data different aspects? Like you're working on the populations and understanding how the evolution took place. There are scientists who are working on other things. So how with just that data you have so many fields that are opening up?
Absolutely. So I should emphasize that with gravitational waves, we're seeing just one little bit of the spectrum, right? We're seeing just mergers from compact binaries, and that's what LIGO, Virgo, Cagra sees. There are other collaborations that look at different parts of the spectrum, and there are other missions in the future that will be looking at other regions of the spectrum. So definitely exciting science, exciting time to be doing gravitational wave astronomy. Like it's just going to grow. But in terms of compact binary mergers, you can get a bunch of intrinsic and extrinsic parameters. So intrinsic parameters being like things like mass, spin, spin orientation, extrinsic parameters like distance to the source, sky localization. And so I care mostly about the intrinsic parameters, the masses, spin orientations, because especially spins, I've done a lot of work on spins. And the reason for that is depending on which way they're aligned with respect to the orbital angular momentum, could actually tell you a little bit about how they might have formed. And so questions we like to ask is like, what is the overall population doing? Do they fall into different buckets of how they formed? So there's two, and to get into a bit of the science of this, there are two main scenarios we consider for the formation of these compact binary systems. Call them the isolated versus dynamical evolution. So isolated means these things are forming in isolation. So you've got two stars in a binary living their absolute best lives together, and then they die together, become black holes together, and merge. And so over their lifetime, the spin orientation, so like these my fingers are meant to represent spin vectors. And so the tidal interactions between the stars allow them to become aligned with respect to each other and respect to the orbital angular momentum, potentially. There are other predictions as well. And, the supernova goes off and collapses, and another supernova goes off and collapses. And there might be kicks that just slightly misalign these, but generally you expect them to be aligned. So if you see that in a compact binary, because the evolution of the black holes, you don't expect any tides, you'd expect them to be generally aligned as well. And so that's a hint that maybe it's isolated evolution. In the dynamical sense, you expect something very different in terms of, okay, these are black holes that have been born somewhere, and they're in dense regions of space. So for example, if you think of a globular cluster, like lots of stars in a cluster, is a very dense region of space, and black holes are heavier things, and they kind of condense to the center. You have these many interactions between all these things whizzing around, and eventually maybe two of them will capture each other and merge. Here, there's no reason why they should be aligned, like any spin orientation. And so when you look at it on a population level, you might have a group that has preferential alignment, and you might have another group that has like an isotropic distribution in spin orientation. So it's like a flat distribution in the cosine of the angle, just a flat distribution, which might indicate, okay, that might be the dynamical population. So you have predictions of what the properties of your compact binary should be based on how it evolved, but also things like masses. And one of the big questions we have is, there's predictions that black holes have a certain mass cutoff from when they form purely from core collapse supernova. And beyond a certain point, you shouldn't have black holes of that mass. And the initial prediction was like around 40-ish solar masses, I think 35 to 45 solar masses-ish. But we've seen black holes beyond that. And so the prediction of where this cutoff lies varies depending on different rates of reactions in stars. So the production of heavier elements in stars, those reaction rates, which I'm not very familiar with. I'll say I'm not an expert in stellar stuff. But it's all these things, these variations actually can push it up to like 70 solar masses. And so there's a huge range. But the other scenario might be, okay, maybe it's just a merger of black holes. But if there are mergers of black holes, you actually expect a pairing of, okay, the more massive objects actually should be spinning faster because you're getting a merger that's, incorporating the angular momentum of the binary as well. So it's going to be a fast spinning thing. So all of these things, right? Different formation scenarios and different stellar evolution processes lead to different properties. So the way we infer it is going, okay, these properties might actually match up with their stellar evolution processes. But there's a lot of uncertainty. But the more events we get, the better we can constrain these things. So that's what I'm really, really interested in, is trying to understand these overall population properties to really try and distinguish these things. And that's the area that I work in as like population studies of these things. Of course, there are lots of things people do with gravitational waves, but this is just one area where we go, okay, these intrinsic properties are telling something about how these systems formed and evolved. And that's just my bias. I really, really like trying to understand how these things lived their lives before they died and became compact objects. And we saw their final moments in gravitational waves.
It's amazing. I mean, you explained it really well. It was as if you were telling me a story and you were telling me the process. It was really good and really interesting work. Really interesting work. Okay, so those were the questions that I had. Would you like to give some last comments to our audience or anything specific?
Um, I mean, if you let me talk forever, I can talk forever. But it's yeah, I mean, I'm super excited about this this latest events that we've published. I got so excited that I decided to make some infographics that I shared with the collaboration to kind of showcase. So I hope people have seen those and kind of hopefully they help give a summary of what these events are like and what we actually discovered. But it is so, while it's sometimes a bit tiring to be on paper writing teams because you've got deadlines and stuff, it's always a great opportunity to work with a different group of people sometimes and get to know them better in the collaboration sense, because I work with mostly populations folks. But when you're on a paper like this, there are people from the detection group and people from different search pipelines and people from parameter estimation. I am kind of in that group too, but it's a huge group of people that you don't usually work with. So it's just nice to meet people. So I've had a lot of fun writing this paper with folks, and I'm hoping that people will have a lot of fun reading the paper. So I'll end there. This is a pretty exciting event. If you have any questions, you can find me on socials. I'm moderately active on there, so you can always get in touch. This is all I'm going to end with.
Okay, okay. Thank you for joining us today and sharing some insightful thoughts for this interview. And I hope we get to interact more through LIGO-India Public Education and Outreach with you.
Thank you so much for having me, and thank you for this interview.